The following is a conversation I had with Marwa ElDiwiny on her podcast on soft robotics, which you can find on any podcatcher by searching Soft Robotics Podcast. I'm excited to bring you the audio here, but I would strongly encourage you to subscribe to her podcast where she talks to leading researchers not just about technical issues in soft matter and intelligent systems, but also issues related to research in science and engineering.
Hello and welcome to IEEE Soft Robotics Podcast. Could you please introduce yourself?
My name is Darren Lipomi. I am a professor of nanoengineering and chemical engineering at the University of California, San Diego.
Thanks for joining us. I would like to go back when you were a child. Do you have any memory that make you interested in science and strike your imagination for where you are today?
Sure, I was always interested in science. My parents were not scientists. They are not scientists. My father's a tailor and my mother is a librarian, but we had a healthy interest in science growing up. I was very interested in Star Wars and Star Trek, like a lot of nerdy kids were. And I had a lot of science toys, like Capsella, which was sort of a robotics kit that had gears and impellers and motors of various types, and Legos, particularly the Technic set. Although I think I got one of those sets well before I was sort of skilled enough to know how to use it.
Interesting. So if I ask you what is the first robot you build, because I know you work now shifting a little bit between material science and soft systems. So if you can tell us, do you have any memories about first intelligent soft robot you built?
Well, I can't claim ever to have built an intelligent soft robot. The first robot that I ever built was a piece of a character that looked a bit like a French fry. He was a plywood character that I made when I was about 5 years old. I drew a face on it with a Crayola marker, and I took a lamp cord and spliced the ends of the wire off, and then just taped the wires to the back of the plywood head, expecting that it would actuate. And my mother told me, that's a great invention, but please don't ever plug that in.
Awesome. So I'm curious to ask you, what is the most beautiful and profound equation that inspires you in your work?
So there's an elegant scientific idea, namely the conservation of energy, that comes in a number of forms. You could think about the first law of thermodynamics, for example. And I think that the conservation of energy on the molecular level, when you're thinking about macroscopic systems, is more profound than I think students and beginning researchers tend to give it credit for. So a lot of times we think about conservation of energy in terms of photophysical processes or balls on a pool table, but it has profound consequences when we're talking about manifold ways of dissipation of energy. For example, friction and particularly adhesion and viscoelastic adhesion. I've been thinking about this a lot lately and how to design materials that dissipate mechanical energy in ways that do not cause a large-scale fracture of the material, and in my case, retention of mechanical function as well. So I think that energy dissipation gets a bad rap because friction is, the sink for so much power in industrial processes. But if you can design dissipative pathways intelligently, you can get a lot of functionality out of them.
Right. So if I ask you how you would define soft robotics from your experience, what could be the best definition? Is it fully soft as a material science? Do you think that should be, or how it looks like for you?
So my connection to soft robotics is a bit more peripheral than I think a few of the other guests that you've had. I did my PhD with George Whitesides sort of when soft robotics was hitting the I don't know if you can call it mainstream yet, but it was becoming greater prominence at the time when I was in the group. And then when I started my independent career, I moved into stretchable, compliant sensors, and particularly the materials of which those are made. And now I'm quite interested in haptics, which have a number of overlapping concerns as the field of soft robotics. I would say what soft robotics means to me is the use of a polymeric material, although perhaps not exclusively a polymeric material, to make some type of intelligent actuating system. But the key point of soft robotics is the materials control, the use of materials to sort of offload some of the function that you would normally that the onboard electronics would normally carry in a hard robot. You offload those functions to the materials so that you have a more elegant solution for certain types of engineering challenges.
And if I ask you what you think maybe the most important question we have to consider, or maybe as a community we have to focus on, and we are not really focusing right in right moment, something we have to shift to focus on.
I think a connection to the materials chemistry is an area that is ripe for innovation in soft robotics. I think that rightly so, the soft robotics community has been dominated by electrical and mechanical and computer engineering, which is fantastic. I think that's where the core of the innovation has to be, but insofar as soft robotics is the marriage of traditional robotics with materials science, I think materials chemistry and design of materials that, for example, exhibit more reproducible stress strain behavior, have less creep, more linear, a longer linear elastic regime, and less loss in the material is those are some sort of mechanics challenges. And then there's the sort of futuristic stimuli responsive types of materials that really are intelligent, that really do need a chemical input and some innovation in synthetic polymer chemistry.
I think I'm curious to ask you this question, since you said sometimes we don't get reproducible result for smart material, and there's many examples like anti-conductive polymer. It has low performance, low response time, and low force, and it's indeed hard to replicate a design or a model. And sometimes you give up about this material, and it ends up there is no realistic application behind it, just to show up in a paper, but in real world we can't use them yet. So do you think it
Yeah.
comes down
Yeah.
to what is the problem? It's just because maybe modeling is not sufficient enough, maybe the fabrication, we don't know, but there's a gap here. How you would see this gap?
I think you've identified a very important problem that in the field of mechanically compliant electronic materials, there are a few ways to go about it. You have stretchable composites that might include some conductive polymer and carbon nanotubes, or maybe some silver flakes, and they end up in a paper, and then the next week you find another very similar paper with a very similar recipe, and there may even be some cyclic loading data or some long-term degradation in conductivity that maybe is not so favorable for a realistic use case, which is why I think we tend to go back to the same tried and true materials, that is metallic traces using serpentine or fractal layouts combined with silicone elastomers that still are not actually the ideal materials because of viscoelastic effects. So this is an area that does demand more attention. I'm not really sure that it's that continuum scale modeling is going to be the best approach to increase the reproducibility on the material side. But it strikes me that a chemically focused approach as opposed to a pure compositing approach is going to be part of the the winning solution.
Yeah. So, if I ask you, do you think the future of soft robotics in general, do you think we have to shift on designing smart materials that are able to compute their energy and force? Do you think that's something we have to focus on?
I think that the ability to design a material that on the scale of the material, or perhaps the microstructure or the millimeter scale structure that can sense its environment and then provide a signal to the material to adapt to its surroundings is quite a pie in the sky goal. We on the material side are quite far away from a material that embodies such intelligence. I would say that for the time being, it's okay to outsource the much of the information gathering capabilities to onboard electronics. But certainly that's a goal of stimuli responsive and so-called smart materials. But in terms of materials that actually embody some kind of intelligence, so the ability to gather and apply knowledge and work towards a goal in its environment, and perhaps have an underlying set of values that undergird its goal seeking behavior. That's quite far away, but in principle, I don't see why it can't be done in some form.
And maybe this question for a student as well. When you design your soft material, what is the most challenging part in designing? When you reflect on the performance and make characterization, how you can identify what is the significant maybe parameter affecting in the behavior, and you have to change design as the material scientist. How you can do that?
Yeah, that's a fantastic question. The biggest challenge as a materials chemist is actually the chemistry, and particularly in an engineering lab where we employ a number of chemistry oriented grad students and postdocs. We really have to get the design of the material right on the first, second, or third try. And I think what ends up happening is the we are a bit limited in the in the synthesis and getting reproducible syntheses one after the other. And indeed, some of the most popular mass market polymers that we buy for soft electronic systems, there is an enormous amount of batch to batch variability, and these are made by professional chemists at companies that we've all heard of, and yet there's still this batch to batch variability. So I think the coming up with a synthetic procedure that works every time in the lab is even more of a challenge for an academic group. So that's a challenge that I would identify.
And if I ask you, what do you think the misconceptions you have witnessed related to soft robotics domain, or maybe in academic world in general, misconceptions related to robotics or soft robotic material science?
Misconceptions in so if we're talking about misconceptions of the broader community toward academic science and particularly academic engineering, I think the misconception is that we should function as the R&D department for the world's technology companies. And I think a lot of times when I talk to some scientists in industry, but particularly in finance, not scientists, but financial people in finance, they are looking for something with a much higher technology readiness level than is the mandate of academic science and even academic engineering. So even as academic engineers and material scientists, our fundamental charge is really to create knowledge and to train graduate students to become to become masterful in the techniques of creating knowledge. And I think that's a misconception that doesn't necessarily just apply to soft robotics, but perhaps it particularly applies to soft robotics because a soft robot made in the lab looks kind of like a product, even though it really might be, a TRL, 1 or 2, as opposed to something that's ready for commercialization.
I think it's a serious point. How do you think we can make this image correct? How we can make sure we're not overselling what we have?
The press we get is fantastic, and we couldn't do what we do without press coverage. I think in some cases it crosses the line into hype, and this isn't usually. It almost is never the fault of the university press department that prepares the original press release, but often when these press releases are picked up by the popular media, the the readiness level and the commercialization potential is jacked up and overhyped. I think so. A little bit more care in not disclaimers, but maybe making the basic science aspect or the scientific breakthrough that enabled the new invention raise the prominence of that and less the flashy photograph or the 10 to 15 year application.
I think also this is very important because I would like to go, since you speak about that, I would like to go, since most academics sometimes were not able to communicate with general public or lay people. And you started YouTube's as well, videos, and lately a podcast. So I think that's quite interesting because as a clinician as well, you not stay in the lab, but you're trying to reach large audience and speak honestly about the problem you have. If you can tell us more, why you think about that very important for you, and do you think it was a challenging for you as a professor as well in your career?
I began my I've always had an interest in video production. Again, when I was this also started when I was a kid. I had a Fisher Price PXL 2000 black and white video camera that could record a few minutes because of the very high data rate on an audio cassette. So you got a few minutes on side A, a few minutes on side B, and you could make these very low cost productions. But it was fantastic because my family didn't have a lot of money. We didn't have a VHS camcorder, so I started to make movies. I was always very interested in movies and special effects, and when I got to grad school and my postdoc, I was working so hard on the science that I let these other interests sort of fall by the wayside. And then in 2007, I became very interested in the active learning methodology that is used in usually a few different professors in a department will use the flipped classroom or active learning method, where they record a lecture and then use the lecture the class period as sort of a variety hour where students do design challenges and so forth. And I wanted to do that, and I wanted to do it for a number of reasons. One, I think I enjoyed the oratory aspect of teaching. I enjoyed being able to share what I knew with an audience beyond just my classroom. And I frankly didn't enjoy rememorizing the same lecture notes every single year for those courses. So I recorded them all, and then around the same time, I started to I became the coordinator for a graduate student seminar series. And this seminar series attracted maybe 80 to 100 students per session. And when I couldn't find, and the professional topics were things like job interviews and public speaking and writing and working with the press and coming up with new ideas and applying to graduate school or postdoc or academic positions. And I started to record those as well. And when I couldn't find a speaker for the topic, I ended up giving the talk myself, and those are the ones that I recorded. And then I just put those right up on YouTube, and I started to get some hits, and a few of them have a few thousand views each. Actually, my YouTube channel is almost up to about 600,000 views in total. At this time, I have over 6,000 subscribers. And the podcast came from basically came from maybe you could call it like fan mail, where they said, I don't want to subscribe to YouTube and pay money to get just the audio on my phone. Can you upload them as podcasts? So then the first several episodes of the podcast are the audio versions of my YouTube videos, but now I've actually started to record some original content as well. And the niche that that I'm trying to occupy is to be of service to younger academics, to undergraduates, graduate students, postdocs, and early career faculty members. And the goal is to lift the veil on this somewhat obscure process of writing grants and speaking and coming up with ideas, fundable ideas, and where to submit your paper and this kind of thing. And there wasn't really anyone doing this sort of full time on the internet, so that's the niche that I think I'm filling. And I have a Twitter account which is sort of to promote this work, and also to sort of point at, in a lighthearted way at the foibles of academic science.
That's very interesting. And I'm curious to ask you, do you think it's challenging to running both of them? I can understand you, it's a hobby for you since childhood. So. But do you think in academia, because I think there's a trend, some people underestimate from the value of podcasting sometimes and see it's not scientific. That's argument. I don't know how you would respond to that.
The reception professionally for me has been quite good. I understand that in the history of scientific communication by scientists, they are sometimes regarded as mere popularizers and people who aren't really making innovations on by themselves. I think you look at the history of Carl Sagan and Neil deGrasse Tyson, now people who have sort of become professional science communicators and haven't really done a lot of their own basic research for quite some time. And I think there's an idea that you have to have either one or the other, but I think I've escaped that categorization for two reasons. One is that my media appearances, my media production is very rarely about science itself. It's about sort of peri-scientific ideas, like how science is done, as opposed to what's going on in my lab right now or what I find interesting. And in my case, the audience is other scientists as opposed to the media or a popular audience. If a popular audience wants to tune in, that's completely fine with me, because I think it's important that people outside of academia know how academic science is actually done. And the other way I think I've escaped the downside of having a public face or a public voice is that society is much more accepting of this kind of activity than it was than it was in Carl Sagan's day, or even quite recently. You know, it's only been a positive on my tenure and promotion files, and now I'm full professor, so I don't really have to worry about any of that. And in fact, if I can show that I've had an impact beyond the boundaries of my campus, it's actually regarded as a good thing.
That's very interesting. And I would like to ask you, do you think that the shape of education has to be changed in that case? It proved that when you have this kind of activities, YouTube or podcasting, it maybe leverage the awareness of people that listening to you. Do you think that the way we education have has to be changed beyond staying campus and receiving from normal classes? You could imagine something beyond that, different way of education.
Yeah, I think that technology will have to play a more prominent role in education, particularly in light of the ongoing COVID-19 pandemic, where universities have been forced to adopt online learning. And However, and there are some arguments where it might make sense to have the best calculus teacher in the world teach, you know, calculus 101, and then we just stop teaching that locally. I actually don't think that's a very good idea. I think it's important that a student have an individual relationship, even if it's, you know, 1 out of 100 students. The level of the the level of knowledge transfer is magnified if you have is really enhanced by having somebody who can look a student in the eye and give them real-time feedback, and also for the instructor to get real-time feedback from the students. So it's a common experience for a lecturer in front of an audience to reformulate an explanation that landed badly or that was misunderstood, and then in real time come up with another example or another way of explaining the concept that finally does land. And in a video recorded lecture, as fantastic as they are, particularly for learning a new topic that's, you know, not taught, or, you know, home repairs or learning to play something on the guitar, you know, it's fantastic. There's no other way to do that. But to learn deep concepts about physics and chemistry and engineering and biology, you really do want to have a knowledge coach that can guide a student. So I think it's complementary, but I don't think that in-person instruction is going to disappear, nor should it.
So we can switch back to your research work related to soft robotics. What's something that you're really interested in right now? Maybe you imagine you want to work in 5 years as a short term. What's your plan for work related to soft robotics you can do?
Sure. So as I mentioned, my research interests are a bit peripheral to soft robotics, but I do have a number of overlapping interests with the community, and those are in the area of haptics. So haptics are technologies designed to interface with the sense of touch and kinesthesia and proprioception. So the sense of touch is mediated by nerve endings in skin, but in a robot, that's a sensor. And in a biological organism, the sense of kinesthesia, that is the sense of motion and force, and proprioception, which is a related concept that refers to the knowledge of position of a limb in three-dimensional space, or body part in three-dimensional space. That information is generated from similar nerve endings, but they're located in the musculoskeletal system as opposed to in the skin. So I have two interests here. One is to use material science to understand the human tactile perception. So most work in the field of haptics uses static surfaces, most haptic devices use off-the-shelf types of actuators like vibrotactile motors, electrotactile stimulators, resistive heaters, this kind of off-the-shelf device. But I think there is a much larger gamut of potential experience, tactile experience to recreate if one has control over organic structure in the real time, in real time. Because if you think about it, the every tactile interaction we have with the material world is mediated by an organic material. Even the surface of the ocean or a desert rock has some adventitiously absorbed biological species or volatile organic carbon molecules that have bonded. So if we can capture some of that complexity in haptic technology, then I think we can recapitulate a much wider gamut than is currently available with off-the-shelf materials. In the field of soft robotics, to recreate tactile sensations requires things like pressure sensors, temperature sensors, and so on. And I think that the community has a pretty good handle on those types of systems because there are so many, capacitive tactile sensors and so forth in the literature that are also stretchable and so forth. I think one area where the field of stretchable electronic materials can make a contribution is to give robots the sense of kinesthesia and proprioception, that is, to design types of flexible, stretchable sensors that behave like the mechanosensory neurons in the musculoskeletal system in a biological system that convey information about positioning and force and so on. And I think it strikes me that that's a little bit less developed in the soft robotics field than the tactile sensing.
Yeah. So if I ask you what do you think the biggest technological roadblocks maybe in short term and a long term for soft robotics field?
So yeah, as an organic materials chemist, you have I have one tool, and this is my nail. The one tool is a hammer. I would say that eliminating viscoelastic effects, improving linearity of the materials themselves, that's a key challenge. I think for a long time there was an idea that you had to untether a soft robot because there's always some pneumatics that are kind of off camera that are powering the device. That's probably not going to be entirely necessary, because I think that instantiations of soft robotics that are sort of most immediately commercially applicable will be integrated into traditionally hard robotic systems where you might have a soft robotic appliance that can be powered on board by the hard components. So I think that's maybe less of a big deal than the idea of tethering or untethering is not as big a deal as some people think it might be. And other challenges. We'll leave it there for now.
Yeah, I think you said something very interesting, and you may be the first one to say it. You want that to eliminate viscoelastic and make the material linear. I think that's very interesting, and thank you for highlighting that. But as your supervisor, Professor George Whiteside, he said in the podcast that nonlinearities can bring opportunities to the material, and I think it's interesting because even for any conductive polymer, it has viscoelastic behavior, and they have higher Young modulus, and at the same time they are soft. So why do you think that we have to eliminate viscoelastic property and make it linear? Why do you think that?
Yeah, so far be it for me to dispute anything that George Whiteside said on this podcast. But I think we're talking about two types of nonlinearities. There's sort of the useful nonlinearity of buckling and snap through effects, and those are actually cases where you can leverage these huge nonlinearities for an effect that you just can't get in in a metal slab or a piece of silicon. However, there are confounding effects, nonlinearities, and those have to do with viscous loss in polymeric materials, and also response times that are short, that are longer than one might hope for, and also the fact that the stiffness of the material, or the stiffness of a robotic appliance, will not be linearly elastic over presumably much of its usable range. So PDMS will be linear for, at most 10% of its stress strain curve, and then all bets are off. And viscoelastic effects are quite well known. If you take a penny and you put it on, well, this is creep. If you take a penny and you have in the United States Abraham Lincoln's head on it, and you put it on the PDMS, and a day later you take the penny off, that impression will be in the PDMS for days, in the absence of an external, restoring force. So this is a serious problem for conventional silicone elastomers.
So, if I ask you to which level the developers of robotics do you think is intelligent, or how do you see they have to be intelligent from your perspective?
This is quite far beyond my expertise. I think, but I'll sort of give you my opinion. The I think obstacle avoidance and that kind of quasi or apparent awareness of one's environment is one manifestation of intelligence on the part of soft robotics that derive from the material, or a simple combination of materials or materials-based devices, like the use of optical waveguiding and so forth in soft robotic appendages, impart some degree of intelligence or situational awareness. I think the vast majority of the heavy lifting in intelligent soft robotic systems comes from integrated circuits, and it will still be that way for the foreseeable future. It's hard to imagine. It's hard to imagine forming something like a synapse in an organic structure. But of course, biological systems provide the proof of concept, and there are a lot of forms of intelligence in soft biological systems that actually don't involve the nervous system. So, in one example is the way in which shear stress in the endothelium in the interior of blood vessels produces metabolites, like carbon monoxide, or I'm sorry, nitrous oxide, not carbon monoxide, that travels downstream and then signals other molecules in the vasculature to sort of release their tone. And that is a way of regulating blood pressure without involving the nervous system. And one could envision ways in which sensing and actuation in material-based systems are coupled in a way to give some rudimentary intelligence to the system in a way that circumvents the need for integrated circuits. And I think that is a really important area of research.
I'm curious to ask you this question because we see also for robotics there is a trade-off between the mechanical performance and response time, taking into account the morphology of robotics. So, for example, if we have a smaller thickness, you will have lower force but fast response, and vice versa is true. How do you see these trade-offs, and how can we have a system that have fast response and higher mechanical performance at the same time?
That's that is the key question. And in my own research, we have a similar problem. What we are trying to do is improve the mechanical behavior of semiconducting polymers. And a semiconducting polymer is a polymer in which every other bond between carbon atoms is a double bond, and this bonding arrangement permits the more or less free flowing of electrons along the backbone under the appropriate stimuli or doping level, or there are many ways to do it. The problem is the types of molecular structural motifs that give rise to semiconducting behavior are also anathema to mechanical response, which is a big problem because this whole field is designed for, or is looking to a day in which we have foldable OLED displays and biosensors that are skin conformable, and solar cells that can be stepped on and printed in a roll-to-roll manner. So it's a big problem, and this is actually the problem on which I sort of started my independent research career. And most of our solutions at the beginning were dedicated to or had the character of finding the razor's edge. So how much compliance is too much before you lose a useful level of electronic performance. And there were only a few cases in the literature, and our lab had one of these discoveries where it was legitimately possible to achieve the best of both worlds. And in this case, it was a chemical innovation where we had a semiconducting segment of a polymer and then covalently bonded a polyester segment in kind of a multi-block or we called it blocky copolymer. And what happened was that the more stretchable polyester you added to the system, not only the more stretchable it got, but the more the better semiconducting properties, the higher the charge carrier mobilities were in the material. And this was a completely non-zero sum interaction, and it had to do with the level of phase separation that we were inducing by adding more and more of the weight fraction of the insulator. It actually drove the formation of these fibrillar aggregates of the semiconducting material that actually allowed it to form a percolated network that wasn't possible in the case where you had a much smaller loading fraction. So I can't solve the elastomer problem off the top of my head as it concerns soft robotics, but I think the take home is that you have two approaches. One, you can find the razor's edge, the sort of frontier area where one property does not, optimizing one property does not catastrophically destroy the other property, or you can look for ways of achieving the best of both worlds through the judicious use of polymer physics and chemistry to create materials that respond with orthogonal processes. The one final comment is that in that case, it's relatively a simple matter because you have an electronic property on one hand and a mechanical property on the other. However, in soft actuators, it strikes me as a more difficult problem because you're trying to optimize two properties that are fundamentally mechanical. That is, force generation and modulus.
I'm curious to ask you to which level do you think descriptive model for smart material in general is really helpful or not? Because we see maybe sometimes we see modeling is not appreciated and maybe not really capturing what happened in the real physics in the material. And I'm asking this question because you highlighted something interesting about the previous question in your answer. But when you go to the modeling scales, you're more interested in micro scales, though, microscopic scales. And in soft robotics, more concerned about the continuum level. So do you think we can, because it's really maybe a gap or maybe a challenge if we wanted to apply control later on, do you think we can combine the micro scale modeling with continuum scale modeling? Or is this challenging? Because it's still a gap. I don't know what you think about that.
This is a huge challenge, and I'm not a computational scientist, but I do have computational collaborators and colleagues. It strikes me that the the problem is one of parameterization of the continuum scale models with an accurately parameterized molecular model. And molecular modeling in the design of soft materials is actually quite a bit farther behind molecular scale modeling of hard materials for energy storage and conversion, for example. We're not yet at the point where we plug in some parameters that we want, or use AI algorithms to plug in some mechanical properties we want, and then the algorithm spits out the properties, or spits out the structure of a polymer along with its molecular weight, tacticity, dispersity index, and so forth, that you would need to get those properties, and only that way could you use the modeling to completely in silico parameterize the continuum model. I mean, of course, you can parameterize a continuum model using empirical data, and I'm sure to the extent that that's doable, people are doing it. It's not my area, but it modeling certainly will be part of the solution for materials design. I think I think it's a ripe area of research to use machine learning to design polymers. I mean, it's a really hard problem, but I think that there's a major opportunity there. And then I think the continuum scale modeling would follow once we have a better understanding of the mechanical properties of the materials on the molecular scale.
I think it's very interesting when you say that for designing polymer. Do you think it's about generative design by machine learning? What could other opportunities do you think could be helpful in designing smart material by machine learning?
I think a closer collaboration between synthetic polymer chemists and mechanics-oriented scientists would, of course, this exists in industry. I would say that it's underdeveloped in academia, where you're designing a material on the molecular scale to achieve some continuum output, some level of adhesion or response time in the case of robotics. I think there are historical accidents in the way that chemistry departments and material science departments and mechanical engineering departments are separated on campus. At UC San Diego, it's a 15-minute walk from the engineering school to the chemistry department, and I think that's a shame, because there's a lot that we can learn from each other, and it really arises from all accidents of history. Even though there is consilience between these fields, we all know it, but we're not in charge of each other's promotion and tenure, and then that actually dribbles down all the way to what science can actually be done. I would love it for I would love it for continuum mechanics folks and polymer chemists to talk more often than it appears they do in academia.
I'm curious to ask you, this may be related here, how we can make sure we have inclusive culture around competitive ideas. Since we know the funding to secure funding and grant, there's a severe competition in academia in general. So how we can make sure that we have inclusive culture while we have competitive ideas?
I would say that the funding environment in the U.S. and its receptivity to collaborative projects is quite good compared to my understanding of how things used to be. Sure, there are still institutes at the National Institutes of Health that are responsible for the funding decisions, but it's actually quite common for them to co-sponsor a project. I think the same is true at the National Science Foundation. The best collaborative projects are the ones that arise from a bottom-up a bottom-up meeting of graduate students at a coffee shop or something, and then they involve their professors later, and then seek funding. The I think it's the university campus, the campus architecture, the administrative structure itself, that are more barriers than funding at this point. I think program managers like to see interdisciplinary proposals. And then there's another institutional cultural barrier, and that is we don't publish in the same places as each other. And even the document types that are considered acceptable for promotion are not the same across disciplines. Let me give you an example. IEEE is the host of essentially all of the haptics conferences in the world, and in an academic electrical or mechanical engineer publishes a competitive conference paper, it gets accepted, that goes on their CV. However, in the material science and chemistry communities, we have MRS, and in America, we have ACS. And the conference papers or published abstracts in those organizations are not used as, you get no credit for those. It's much less than a paper. So you can't survive as an academic on conference abstracts from MRS in the same way that you can be promoted with a conference paper in an IEEE conference, which is a more substantial publication than an ACS or MRS abstract. The way that this becomes a problem is that if somebody is trying to enter the field, for example, of haptics from the outside, how are we going to publish in that community? And this is a big problem, because I wouldn't get the appropriate credit for a conference paper published in IEEE proceedings by my tenure and promotion package reviewers, who are chemists and material scientists who don't have an equivalent don't place an equivalent value on conference publications. So this is a way in which institutional inertia impedes inclusion in the scientific sense.
Yeah, I agree with you. So if I ask you how you can ensure the developed project within your lab, you and your team, is going to be beneficial to the community or humanity as a whole, how you make sure it's happening? What metrics you set to make sure it meeting your end goals for a survey community?
That is as important as it is difficult to address. I think that well, first of all, the laboratory should have a mission and values and convey that mission and those values to students whenever possible. I think that there is the wrong way to do research is to treat it as the wrong way to treat a PhD program as like a vocational degree, where a student comes in and turns a crank for 4 to 6 years, learns how to use an instrument, but then doesn't really know what its societal implications are going to be afterwards, and maybe they're given the project, so they don't really develop a good sense of project selection and how to actually create knowledge. So I think it's important that serving society, making good use of taxpayer dollars to educate students and create knowledge at the same time, sort of as a byproduct, picking the best projects we can that serve as vehicles to training students. These are important values to have in an academic research group. In terms of downstream measurement of our societal impact, there are some quantitative metrics, like if there's a technology that's licensed, and you're judging that the company that is licensing the technology, or that you maybe you started, is having a positive societal impact. That's one way to view it. It's a hard question. Everybody has slightly different values. For example, human machine interfaces versus energy versus healthcare. It's a tough one, but I think it starts with having the right with having a value system in place in a research group and conveying it to the students.
Yeah, I agree there. So we're close to the end. We have just three questions. Do you think ego is important for the researcher?
Ego, there are two ways in which one conceives of the word ego, at least that I conceive of the word ego. One is synonymous with arrogance, and the other is synonymous with the sense of self and ownership of one's ideas and consciousness. And I think that the sort of popular definition of the word ego is synonymous with arrogance. I don't think that's really important. And I mean, well, it may be important for some people, but the less of that there is, the less competitive, the less sort of cutthroat competitive spirit there is, the better. I think that we're not scientists are living in a community. We are not in a monastery on a hill somewhere. So we sort of derive some energy from a sense of competition and being the first to do something. I think that's an important motivating factor, but not in not in an arrogant way, if that makes sense. I think one can be competitive but still have empathy for for the other people in one's community. I think the more subtle definition of just the sense of self and ownership, I think that is incredibly important for any creative act. The idea that as a researcher you're building equity in your career in the form of inventions and publications and knowledge created and students trained, I think that's very important for anyone that goes into research or any creative endeavor. And I would hate to think what would happen to the scientific enterprise if you took that sense of ownership and agency and away from scientists. It's a bit like if you take away somebody's the gene for somebody's Pacinian corpuscle in their fingers, they don't die, but they have a severely reduced experience and may have to just navigate life some other way. So it'd be a dangerous experiment. I'm not sure I would want to see the result.
That's important, yeah. And if I ask you, what is the most important quality you have gained while you're working in academia, and something you have to maintain in your journey as well?
Before I started my independent position, I had the perhaps misconception that every interaction I had, or every paper I wrote, or every grant I wrote, had to have the primary goal of getting the money or sounding smart or getting the paper or showing the world how good my idea is or was. And lately I have taken another tack, and I think if one creates if one has the goal, instead of delighting the reader or the audience and creating a sense of satisfaction or a sense of feeling smart in one's conversational partner or reader or viewer on YouTube or in the classroom, then all the good stuff will flow from there. And it has the advantage, such a mindset has the advantage that you can be successful every time, even if you don't get the grant or if the paper gets rejected. If the goal is to delight the audience, to instruct the audience, to improve their well-being, increase the level of intelligence as the result of a conversation for both people, then I think that's a much more satisfying goal as someone who is involved in learning and research than just getting the grant or getting the paper accepted. I think those will be byproducts if the other person is delighted because they feel smarter after having read the grant or having watched the video or listened to the podcast.
I think that's very important and powerful message. I thank you for that. And lastly, what was the best advice was given to you, whether personally or professionally, and was life changing for you?
I think the best advice is probably some advice I didn't take. And maybe I was told by both my PhD advisor, George Whitesides, and my postdoc advisor, Shannon Bao, not to ramp up too quickly because you're going to have too many students early if you hire a lot of students out of the gate and not have enough funding to pay for them. And then you'll have a lot of sleepless nights. And I probably ignored that advice, and perhaps to my detriment, but these are the kinds of things that you have to, and this is incidentally the advice that I give my younger colleagues as well. But I think perhaps better advice would be, it's okay if you have to learn things the hard way. Everybody has to learn things the hard way, but don't beat yourself up for it. You can listen to advice and it maybe moves the needle in your own thinking 5%, but making a mistake moves the needle 99% of the way. And that the knowledge and wisdom that one gets from the actual experience of failure is much more important than the advice itself. So I'll revise my advice by saying that the best thing is to accept that failure and rejection is the only way to really change your behavior.
I can't agree more with this advice. I think that's something everyone has to learn. Thank you for that. I would like to thank you for your time. I really enjoyed this discussion. Thanks so much for your time.
Me as well. Thank you, Marwa.